electrons, it would be carbon 14. Okay, so let's go back the other way. If I had O for oxygen, which it has 8 protons, 16 as its atomic number, its number of protons is 8, its number of neutrons is 16 minus 8, which is 8. Okay, so if I had hydrogen, atomic number 1, and it had an atomic mass number of 3, a number of protons is 1, a number of neutrons is 2. This is such an important isotope, it has a special name, it's called tritium. Don't have to memorize that, just giving you a little chemistry trivia. So, atomic symbols. All right? So there's a couple of examples. Now, if we look at an element, a sample of an element, let's say of carbon, okay? The isotopes are not equally portioned. There's usually predominantly one isotope that's more common than the others. So we talk about their percent abundance. So if I had 100 atoms of element X, let's say 60% of that element will be isotope 1 and 20% of it might be isotope 2 and 20% of it isotope 3. Okay, so percent abundance. So that leads us to something called atomic mass. Notice this is not atomic mass number, this is atomic mass. Atomic mass is the average mass of an atom of a specific element. Okay? And it's based on natural abundance. So, what percentage of the overall number of that element do we find? Okay, so we're going to look at an example problem of calculating an atomic mass based on an isotopic mass. Now let me give you an isotopic mass. This is the mass of an atom of a specific isotope of an element. Okay, so atomic mass, isotopic mass. Both of these are in AMUs, atomic mass units. Okay, atomic mass unit. The atomic mass unit, 1 AMU, is 1/12 the mass of a carbon 12 atom. Carbon 12 is called the atomic standard. Okay, and that's because it's very, 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 very stable and it's very, 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 very common. So they shoot a carbon 12 through the mass spectrometer. They see where it diverts when it goes through the machine, and then they look at where everything else diverts relative to carbon 12. So 1 AMU is 1/12 the mass of a carbon 12 atom. Okay? Now, we're going to look at a sample problem to go from isotopic mass to atomic mass. So we're going to look at chapter 1. We're going to look at practice problem 1.4. Okay? And it's on page 55 in your textbook. Now, if we look at the practice problem, it says that magnesium has 3 naturally occurring isotopes. So, magnesium has 3 naturally occurring isotopes. One has a mass of 23.99 AMUs. One is 24.99 AMUs. And the other one is 25.98 AMUs. Okay, this one makes up 78.99%. The middle one makes up 10.00%. And the last one, 11.01%. Okay? Now, I've got all of that in there. So how do I do this? Well, first thing you want to do is you want to convert these percentages to decimals. So 0.7899, 0.1000, 0.1101. Remember, to go from percentages to decimal, you just divide by 100. So all I'm going to do is go 23.99 AMUs times 0.7899, and I'm going to add to that 24.99 AMUs times 0.1000, and then 25.98 AMUs times 0.1101, and I'm going to add those all together. So let's do this. So 23.99 times 0.7899, that gives me 18.949701. I'm going to worry about significant figures at the end. AMUs. 24.99 times 0.1000 is 2.499 AMUs, and 25.98 times 0.1101 gives me 2.860398 AMUs. Now, if I add these up, 18.949701 plus 2.499 plus 2.860398, my calculator is reading 24.349099. Now, when I do this, I'm limited to 4 significant figures. So when I add, I'm going to have to end in the hundredths place. So I'm going to have to add in the hundredths place. So that puts me right there. So I'm going to report 24.35 AMUs. And this is the atomic mass. It's an average mass of elements of that atom based on relative abundance. Okay? There's a second problem, 1.4 on page 55. You guys can work that on your own. The answer is at the end of the, no, it's at the back of the book, so you can check it. Okay? So, expect some of that in your homework. Now, some other things that we're interested in about an atom. We can talk about an atom being neutral, or we can talk about ions. Okay? in a neutral atom, which means no net charge. The number of protons equals the number of electrons. I have as much positive as I do negative. When an atom is charged, the number of protons does not equal the number of electrons. Okay? Now, to charge an atom, we either lose or gain, or we either take electrons away from it or we give electrons to it. Okay? Remember, the electrons are somewhere outside the nucleus, and they are moving. The nucleus contains the protons, and that's very deep, deep inside the atom. So the protons never really see the edges of the atom. They communicate, but they don't ever go out there. So if we're going to charge up an atom, we're either going to have to take electrons away from that atom because the electrons make it out to the edge, or we're going to have to shove extra electrons in because there's lots of space around the nucleus for more electrons. Okay? So if the number of protons is greater than the number of electrons, electrons were lost. Okay? We get a negatively charged